some reason that title is missing. Right, so we're going to be finishing off systems of PDEs in this session, which is kind of like the second half of last week's lecture. So I am going to go through quite briefly what we talked about. Essentially, single PDEs aren't of much use when we're doing modelling. Okay, we can model quite simple applications, quite simple phenomena using single PDEs. PDEs is where it's really at, where the interesting stuff really comes in. Uses all of those techniques which we've learned about over this term, we can use them for systems of PDEs. Okay. Single PDEs, we've been solving for this function u. So u has certain values, and you've been calculating what those values for u are, and hence you've been solving a single PDE. With systems of PDEs, we now have a vector. So whereas you'll have a function in the domain, is your solution. You'll have several functions in the domain equation. So you have a vector of solutions. As I just mentioned, there's properties of solution techniques which we're looking at, for example, stability. So what's their order of accuracy, what's their stability, grid convergence, all of that governs systems of PDEs. And the system of PDEs which we're going to be example are what we call the shallow water equations. Okay, this is just one of many PDEs, but this is just an example. Similar techniques exist for other partial differential equations. We saw last week what the shallow water equations are is due to the physics of shallow water. What I mean, the water depth divided by a wavelength. Okay, wavelength is the distance between two sort of successive points on a wave. So let's say between two troughs. By the wavelength, if that's less than 1/20th, the water is considered shallow. Okay, and that definition is given by the physics of water. Water, when the depth to wavelength ratio in motion. Okay, as a wave travels from left to right, a neutrally buoyant particle, it would go in a circular motion, and the radius of the circle would decrease as we go further down the surface. When you're down to about a couple of meters below the surface, so you don't actually feel it. So that's the water. What we call intermediate depth water ratio is less than a half, but greater than 1/20. Elliptical sort of motion, and then in shallow water, motion, so it just goes left to right. Okay, and the shallow water equations are only really applicable in this case. And here they are. This is the one-dimensional shallow water equations. They're called 1D because we're only dealing in one spatial dimension. In a minute, I'll be introducing the 2D version. Okay, so two equations. Okay, and with the dependent variables for these is h and u. H is the water height. Okay, so the height above the surface. If you think about the sea floor, think of this as a beach. So what's the vertical distance, the height between the sea floor and what we call the free surface or the surface of the water? That's your h. U is a horizontal velocity. Both in meters, h is in meters, u meters per second. Gravity, obviously pushing the water towards the Earth. That's 9.81 meters per second squared. We have two equations. This first one is conservation of mass. Okay, so it looks quite similar to the advection equation. So h differentiation with respect to t plus h times u differentiated with respect to x equals 0. H times u is momentum. That's mass times velocity. So how much water is being sort of pushed along? What's that force? The second equation is conservation of momentum. Okay, where h times u this time is your conserved, what we call a conserved variable. So that's what's the derivative of that with respect to t. You've got this sort of expression here. So anything, sort of these two here, which are differentiated with respect to x, then known as the flux. What's the movement? How does the movement change over time? And ZB is just that sort of what's the height of the bed surface above sort of a level. Okay. For our intents and purposes, we're going to ignore that and assume it's 0. Okay, so that was the system. That's an example of a system of PDEs. Now, it's quite handy to actually write systems using what we call vector notation. So we're solving for h and hu. Okay, so I'm going to write that as a vector u. So I have a vector u, which is simply h and hu. I have what we call a flux vector, which is these two. So what I'm differentiating with respect to x are my fluxes. And I've also got a vector of source terms. And as I mentioned, we're going to assume that's 0. I was going to say, I'll skip over tsunamis. That's just one application, and we saw that last week. I'm going to sort of go through this briefly as well. For stability purposes, how do we work out our maximum allowable time step? We need to know what the velocity is. Okay. And for the velocity, we choose the maximum possible velocity, because the velocity change. Okay. And last week, we looked at calculating the Jacobian for this system, and we saw that the eigenvalues of the Jacobian were u plus root gh and u minus root gh. What they are they're the fastest and slowest possible wave speeds. Okay, so the eigenvalues are our wave speeds for our shallow water equations. Okay. And I mentioned something about linearizing the system. That's all contained in the notes. So I'm just going to sort of go back over this. Essentially, once you've linearized the system, okay, going through all of this, we end up with these two equations. Now, these two equations are similar to the advection equation. Okay, so you had, in the advection equation, you had u with respect to t plus v times u with respect to x. So that's similar. So u plus gh and u minus gh must be our velocity v. And we use that in the calculation of the maximum allowable time step. So this ensures that our numerical solvers are stable. It means we can use them. Okay, so instead of v, we've got what's the maximum absolute eigenvalue, which is just the maximum of the absolute value of u plus root gh. So we've got to do that at every time step. So we're going to choose different values of delta t depending on what's happening to the water. When the water's not moving around very much, we can use a bigger value of delta t. When the water is sloshing around a lot, our value of delta t is smaller in order to keep stability. Okay, we looked at the Friedrich scheme. Okay, so the top one here is the Friedrich scheme for the advection equation. Okay, with the advection equation, the velocity was constant, so it came outside, it wasn't involved in the derivative. In the shallow water equations, the velocity is part of the flux. Okay, so we don't have a v there. See, there's no v there, but it's included in the flux. It's very, very similar. So that's the advection, that's the shallow water. But notice in the second term, we're in terms of the fluxes rather than u. So apart from that, a very similar scheme. Okay, We can have a couple of different types of boundary conditions. Transient flow, what that means is there's zero gradient across the boundary. What it means is you've got like a quasi-infinitely large domain. So any water, any wave which is flowing towards a boundary will just pass through the boundary as if it wasn't there. If you wanted reflective boundaries, okay, all you do is you set the velocity at the Gauss node is equal to the negative of the velocity of a fluid node. It has the effect of putting a wall at the edge of the domain. Okay, this is sort of relevant to the dam break test. Okay, in your assignment you got a dam break, but then you got it thrown over an obstacle. Okay, and this is a standard test for the shallow water equations. We have two bodies of water, one of height h0 and one of height h1, and they're separated by a partition. What we do is we remove that partition, so totally get rid of it, and the bodies of water are allowed to sort of interact. What's going to happen is, because this one has got a higher value of h, go in this direction. Okay, so you can see here, we have water flows from left to right and creates a ball wave, so like a stem. And because this mass here has been taken from this point, we have a wave which also travels from right to left, and that's called a rarefaction wave or a depression wave. So you can't sort of invent mass. If mass goes one way, you've got to take it from another place. And here's the solutions. If I just go back, the red line is the analytical solution, and the blue line is the Friedrich solution. As you can see, not quite on the money. We have a bit of a gap here where there's those corners. So that's for water height, and we've also got velocity there. Okay. So we have two solutions. When we're dealing with shallow water equations, we most often just plot the height, but velocity can come in useful for example, calculating the force of water. Okay, the Friedrich is a one first order scheme. To extend this to a second order scheme, we saw we can use a McCormack, and this is a two-step version of the Lax-Wendorf scheme. So we have like a half time step. So we calculate this first equation, and that's sort of like halfway to the solution. And then using the solution from the first step here, here, and here, we calculate the solution over a full time step. And that's second order in time and space. And this is a solution. Hopefully you can see it's a lot better than Lax-Friedrich. We still have a little bit of a bobbly, sort of oscillating type thing here. Okay, that is a feature of second order schemes. It's very difficult to get rid of that. And there are more advanced techniques to do that. We're not going to be... okay. And that's, yeah, velocity as well. Okay, so that's the 1D case. Okay, things become a lot more interesting when you move to 2D. You actually see sort of more of a fluid motion. In 1D, it looks a bit of anti-intuitive. For example, when I was doing my PhD, I showed my friend this graph, or one similar to that. He goes, "I've never seen square waves before." And since that time, he's never let me live it down. So I said, "Oh yeah, I do water, and here's some solutions." He said, "I've never seen water do that." To be honest, he has got a point. Doesn't look that much like water. Okay. So what we're going to do is have a look at 2D case. Hello? I click. Oh no, spinning beach full of death. Something's going on in the background. What have we got? Just done a bit wrong. Rid of the spinning beach full of death. Back. Oh. There you go. Okay, so Right, we're now going to move to. Now, 2D shallow water equations have 3 equations. So 1D had 2 equations, 3 equations. And the reason they got 3 equations is we're solving for the momentum in the x direction, which is HU, is 1D, the y direction. So here, U, in the x direction, maybe left to right, is velocity in the y direction. So we've got 2 sort of spatial directions, x and y. Another equation, so we've got 3. Therefore, we have 3 fluxes, which is the flux. So there you can see it's differentiated with respect to x, and you've got G, which is flux in the y direction, with respect to y. So you can see you have 2 fluxes now, F and G. Actually, they're quite similar. V squared plus RTA squared HUV, the V squared plus RTA squared. So you can see there are some similarities there. Vector of source terms, again, quite similar. It's extending out to another. Weeks ago, we saw what we can use dimensional splitting. That's exactly what we're going to do. So what we're going to do is we're going to solve in one direction. So in this case, we solved in the y direction first, or you could solve in the x direction first, what I normally do. Okay, so we split it up. McCormack scheme, a 1D McCormack scheme direction. Down on our sort of domain, we've got lots of 1D tips, and we're solving for each one of those stripes or rows. And then we revert, then we do it in the other direction, we do it in the y direction. First thing we need to do is calculate what's the maximum allowable time step. Now we're dealing with 2 different directions, we're dealing with 2 different velocities, we're dealing with u and v. Calculate what's the maximum time step in the x direction, 1D case. And we also do the same for the maximum time step in the y direction. Delta x on the top, got delta y. And instead of u there, you got v. There's a very subtle difference between u and v, but it isn't. It's very easy to get those 2 mixed up. But that's velocity in the x, velocity in the y direction. Those 2, and you just smallest one. No good being stable in one direction if it's not stable in the other. Okay, so we performed 2 different sweeps. Okay, so we solved in the x direction first. Sweeps are pretty much the same. Calculate boundary conditions and flux vector. Steps. Once you calculate the predictor, we have to recalculate corrector, and then we update it. That was your 1D solver into that x sweep. And we do exactly the same, but this time in the y direction with the flux vector G. Okay. Using these values which you just calculated. Exactly the same, but in your y direction. And then once you've done it over the x direction, you've done it over the y direction, you've done it over a full time step. So when we've done it over a full time step, we update our time. And we repeat steps 1 to 4. So that includes time step, because that will change. We do that until we get t is equal to t max, or when we want to stop. Okay. Okay, so validation, remember, is we write a program, we validate it. So this is what you do, what you're asked to do in your assignment. So I've given you a program and I said, okay, validate it against some lab experiments. What I'm going to do is I'm going to use the 2D solver to do what we call a quasi one-dimensional downgrade. So what this is imagine you're looking down You have an X direction and a Y direction. And what I've done is all of this region here has starts off with a height of 1, and I've got a height of a half down there. If I was to take a slice across anywhere horizontally across here, same solution. There's no change in the Y direction. And I could also do the same, but for this one, for the other direction. So if I was to take a slice vertically, compare it to any other slice, there will be no change. It's what we call a quasi one-dimensional dam break. 2D domain, only solving it for 1D dam break. Here we have the solutions. Okay, so I have an X axis there and a Y axis there. And there's my height. Okay, so if I was to take like a slice, you'd have a 1D solution. And you can see there's no movement, there's no, all of these lines are parallel. Okay, similar, when I do set up the dam break in the other way, this is here, that's my Y-axis, there's my X-axis, and if I take a slice along that direction, it would all be the same. So that sort of tests, is my dimensional splitting working? From that, it is working. What I might do is actually, if MATLAB has decided to load, let's show you a bit of the code for that. Oh, this bit there. Here we go. I was saying I was doing this quickly. This computer is running very slowly. Okay, so I'm just going to show you a bit of code just to show you that it's not too. Well, hopefully you don't think it's too difficult. It's not something you'll be asked to do, by the way. Okay, it's not loading. Come on. Oh, dear me. Oh, it's not having any of it today at all. I think it gets stage fright. Wow, okay, that's not working. That's a shame. Okay, so might as well just go back to the slides. Okay, so what I've got here is I've taken those slices, as I mentioned, and what I've done is I've plotted the solution when I had the dam break going in the X direction with squares. I plotted the same solution when I had the dam break going in the Y direction with asterisks, and you can see they're bang on each other. Okay, so that just shows that they're both working in the same way. The dimensional splitting is validated using this case. Okay, because we've got two domain, I could have a look at a few more examples. Okay, this is what's called Gaussian Curve problem. Essentially what I've done is I've set up this sort of bell shape in the middle of a square domain. So this is sort of your water surface, and I've created a sort of spike in the middle. So sort of imagine you've thrown a pebble into this water and it's sort of sunk down, gone up, and then the ripples are going to go out. Okay, so there's a contour plot of the initial conditions. So the height in the middle, so this is at 1.5. Okay, all this water here is at 0.5. Okay, and then those are the initial conditions. So the velocity in the X and Y direction, both 0. I just changed the height to be just like a Gaussian curve. Okay, that's the solution after a bit of time. Okay, so what's happened is the water started to propagate outwards. Now, theoretically speaking, this propagation should be the same in all directions. So we should have circular motion. It should just be extended out. So what I've done here is I've plotted the contour. Okay, and it's pretty much circular. There are a couple of things here, okay, which is not quite the same. As you can see, it's sort of circular, flowing outwards. Okay. What I've now got is, hopefully, I want to show you an animation of this, is I've moved the spike so it's closer towards one corner. And what we have is all of the wall boundary conditions. So what's going to happen is they're going to act like a sides of the tank. As you can see, it's starting to happen here. As the water collapses, it's going to reflect off these two sides and sort of propagate over the domain. Now, hopefully, MATLAB's going to, and I don't think it is. You swine. I'm going to give it one more chance. Slowly. Oh, it's a shame. It's no fun without a bit of animation. Nope, that doesn't like that at all. Yeah. Yeah, spinning beach wall of death. Okay, we'll have to just imagine this as being we'll have to imagine this as being an animation. So what we have here is, okay, it's just starting to bounce off. So this is sort of collapsed. These ripples are extending outwards away from the center of the sort of spike. Okay, and this one, okay, you can see they've bounced off this side of the tank. So this region over here is just allowed to flow in the outward direction. This region here is sort of flowed into the wall and then bounced back. You can see we've got a couple of sort of waves coming here. I'll let it flow for a bit more. See the way it's starting to propagate. And we've got all this stuff bouncing off the walls. MATLAB, one more try. I don't know what's gone wrong with it. It's not having any of it today. You set these things up, you're hoping they're going to look good, and then it just doesn't work. Okay, I know what I can do. Okay, in true Blue Peter style, here's ones I created earlier. Oh, these aren't going to work now. Oh, I set all this stuff up, ready to go, and it doesn't work. Come on. If I ever tell you I like MATLAB, remind me of this. Spinning beach ball again. What the earth is going on? Oh. Doesn't like something in the background running. Something's running in the background which is stopping it from doing anything else. Hang on. Come on. Maybe it's the old YouTube thing screwing it all up. I'll stop that if I can. Sorry about this, bear with me. Can't do much while it's still doing this. Oh, come on. Stop it. Oh no, still going. Right, I'm going to give it a few more sets. You know, there's no point me trying to. I might have to reboot the machine. Oh, you swine.